Our next speaker joins us all the way from engineering campus.
Yes.
And he's speaking to us about water management in a time of much rain.
Okay, can everybody hear me? Okay, yeah, so as has been said, I'm a PhD student here at the university working in the Hydroclimate Extremes Research Group with Professor Daniel Wright. And today is an appropriate day to kind of showcase some of our work on flood modeling. But I primarily want to talk about a trick I kind of figured out on working with some of the HTCondor and DAGMan pipelines that I found pretty useful, and we'll kind of talk a little bit about my work, but the focus will be mainly on that. So to start off, I'd like to give a little background on our work. So we're using this technique called storm transposition and pairing it with rainfall runoff models to really get at rare storm sizes and their flood capabilities. So when engineers are designing things, they're looking at rare events on the 100 or 1000 event time scale, and then they compare a rainfall runoff model with that precipitation event to measure the resulting flood. The issue with this sort of pipeline is that when we look at gridded precipitation data sources, we only have around 50 years of data. So for most basins and watersheds, we're not actually going to have the 1,000-year rainfall or flood event in our time series. However, mathematically, there likely are 1,000 events, 100-year events somewhere around the country, typically in the same region. So this stochastic storm transposition, or SST, is a technique of moving storms from nearby, putting them over our watershed, and then we can plug those events into the rainfall runoff models and get resulting stream flow events from that. So we create these synthetic extreme event catalogs. So to responsibly do this, we have to determine what's called a transposition domain, which is the area around a watershed that has roughly similar precipitation characteristics, enough that it's valid to move the storm from its original location to somewhere on the watershed. This procedure is being harnessed by FEMA to update the National Flood Insurance Program across the country. So determining how to draw these transposition domains is really important to do it in a repeatable, justifiable way. So we have developed the spatial L moments of annual maxima methodology called SLAM, which will automatically draw these domains for a given basin. So to do this, we've harnessed HTCondor. For our original study, we looked at 3 basins and are currently scaling it up to 215 basins. So we have to run through this whole kind of 5-stage pipeline to get to a final domains and then the actual stochastic storm transposition piece. We run through kind of the first stage for every basin individually, and then the subsequent steps are repeated for different storm durations that we might be interested in. But I want to point people to this first step here, this calculation of watershed average precipitation from point precipitation, because I think it really encapsulates what high throughput computing can do. For each basin, we need to calculate these watershed average precipitations for 17,000 daily precipitation files, typically sorted into batches to have like the optimal runtime. So we're oftentimes running 1,000 jobs per basin at a time. How this job actually looks is we take a map of hourly precipitation accumulation, and we've reverse engineered the storm transposition process. So we're just going to slide our basin shape across the precipitation domain and calculate the average precipitation. When we look at the 47 or so years of data we have, that's roughly 400,000 hours of precipitation data, and we have to do this sliding for all 215 watersheds. So this is very parallelizable and one of the good uses for throughput computing. So when we do this, we're going to figuring out how to batch it optimally. So we'll likely want to use at least daily batches of files, so we're not transferring the same daily file to multiple jobs, but we need to optimize to make sure we're in like a 3 to 5 minute runtime per job. So this is kind of the first stab we took at developing submit files for this process. So I've taken out a lot of the pieces of it, but the main lines to point people to are the transfer input files and the queue files at the bottom. So this, I think, is a pretty common way to queue different values for different jobs, but you can queue variables from a CSV file and have them be variables in your transfer input files, and it would transfer each line each day into the job. So this worked pretty well when we first were developing the code, but we kind of ran into a few edge cases that I wanted to develop something that worked its way around. So if we're using different resolution data sets, sticking to 5 files per job isn't necessarily optimal. So we could be working with a 1 kilometer resolution data set all the way up to 16 kilometer resolution. So those processing times vary significantly. So we might want 1 file per job for the 1 kilometer and 15 files per job for the 16 kilometer or even more. So that's just kind of one of the issues we're dealing with. What if our total files isn't divisible by 5? We can't easily split it up into a CSV. And then what if we only want to run a select kind of set of days? How would we do that? So probably the most straightforward way to do this is just to create submit files that kind of match what you need it to do. And then you can also create codes that would manage the CSV files themselves. But I really wanted to try and come up with a way where one submit file would work for any number of configurations for a job. So that's where kind of these dynamic input submit files is what I've called them, kind of came out from. So to make these, we just remove the transfer input files lines from the submit file and then replace the queue line with this queue transfer input files from a text file. So you can just choose, you can fill a text file with lines that have all of the input files you would need for a job, and you can just queue from that. So that we're able to create a code that takes an input where we say, these are the dates I want, these are the number of files per batch I want, all of that, and it will populate a text file that we can give to our submit file. This allows us to use the same job scripts, so submit files, executables, Python codes, regardless of the batch size, which is really useful for these different resolution data sets and rerunning portions of a time period or something. It also is much more flexible than that. It could let you run the same, run different watersheds with the same submit file at the same time, different Python scripts, even different numbers of files per job if you were really trying to optimize things. When we first did this, we were only looking at 3 basins, so it was really easy for me to just manually kind of guide things through the process, check when files were missing and update them. However, our new work has expanded from just the 3 kind of pilot basins out to all 215 basins in the US. So this becomes a lot more complicated from a management standpoint because it's pretty much impossible to do this by hand. So that's when we implemented DAGMan, which worked really great for splitting the jobs up into nodes and then controlling the pre-processing, submitting the job, and then the post-processing. So the issue we ran into, though, is for processing the data, we want to make sure that every single output file exists, isn't corrupt, all of that sort of stuff. But sometimes outputs do end up going missing, and it's kind of hard sometimes for DAGMan to detect and react properly. So here's kind of that initial manual workflow. We create the input file list of the files with the batch size we want. We submit the job. Then when all the jobs are done, it checks for the missing daily files, and can then tell it to regenerate the list and then resubmit the job with just the missing files, which saves you time from having to repeat everything or that sort of thing. And then once we get through and have all the files, then we can go through our post-processing and move on to the next step. So DAGMan does have some capabilities as well as our submit files to retry the jobs, and then there's periodic releases and that sort of stuff. So there is stuff built in that does manage a lot of the issues we run into, but sometimes it's just we wanted to make sure all the files were there. So this was kind of a redundant system on that. Another note is if output files are really important, you can put the transfer output files in your code, and that will make sure the files are there. But just with how the outputs changed, creating those lines was kind of difficult. So when we moved to DAGMan, there's really kind of only one change we had to implement, which was adding our in our post-processing step, adding a check on checking what files are there or not. So we start off at the top with the input text file, which has 1,000 lines for 17,000 daily files we run through, and maybe we're only missing 2 files. So the first step of the post-processing goes through, checks our outputs, and narrows it down to just the 2 daily files we might have. And then it gives out a retry flag. It fails the job, so it goes back to the start of the DAG, or the DAG node. Typically at the restart, you would just do the full node. So if we don't change the file, then it's going to retry everything. This instead makes it only retry the 2 files we need, saving a significant amount of resources. So when we do this across all the basins, we just save an incredible amount of computational time. Then we go through. Once it finishes with no missing outputs, then we'll move on similarly to how we did before. So this I just kind of showed one stage where we looked at daily precip files, but this sort of framework is really usable for any sort of method where you're having lots of data. So different parts of the pipeline are checking that we have files for every year. We even do kind of a spatial chunking piece, so then it checks that every spatial chunk is there. So it's really kind of flexible to do with it what you want. Some final thoughts. So the set of job codes does need to be written in this kind of flexible manner. So if you have an input file that can take in lots of different types of data, your Python codes also need to be able to open those. So in this case, we might have our AORC data set that works fine, but then if our input file can input CONUS 404 data, you want your Python codes to also be able to open those data and analyze it. And then there's also, if you have a blank input file, it doesn't necessarily not submit any jobs. It submits one job without any input. So you just kind of need to be aware of what's going on there, because if you do that, your job will probably go on hold. To summarize, you have the batch stage read its list of work from a file, and then it runs through that file and then updates the file based on what outputs are there, and then repeats until you have all of your outputs, and then you move on. So with that, I'm done. My email's up here if you have any questions about how to get this working, and I'd like to take any questions.
Great talk. I'm glad you were able to figure out DAGMan and make your pipeline work the way you wanted to. But you know, as Marone would say, we can always get praise. But tell us what's wrong. Did you have any struggles trying to learn DAGMan, like get into it, or the functionality that you wish was there that just isn't?
I don't know if. So I think that one of the other stumbling blocks I ran into was resource allocation. So when we're talking about using different data sets or resolutions, you want the resource requests to scale with the data. And so that piece was kind of difficult to figure out. I think there are ways now more, I think they have been implemented that you can change your resource requests in the job if it fails or goes on hold, you can scale them. But that was kind of an initial thing we ran into.
Along the same lines, but do you see any of what you were doing as applicable in a more general case, that can we import some of what you are doing as a primitive into DAGMan? So I will admit that I didn't fully is a strong word, follow the idea of how do you manipulate the input files and the number of files and things like that. Is any of this file algebra possibly something we should consider to embed part of it into DAGMan, so those who follow you will need to do less scripting?
Yeah, I mean, I think any sort of implementation that somehow DAGMan also tracks like expected output files somehow, which I think like the transfer output file list in your submit file kind of does that, where it does give you a list that is expected outputted of files. So something like that expanded to a whole DAGMan. And then further, if a node fails, that it doesn't try to just redo every single piece of the node, but would have targeted pieces.
So if you have any thoughts and available whatever time to talk about it, I'm sure that Cole will be strongly excited to hear. But let's think about how would you express it, not by writing a script.
Yeah.
Is there something declarative that can be done to capture some of these operations in a way that the call can offer it as part of the DAGMan? Because it feels like you are not the only one who is facing this when you have to explore a space like this.
Thank you.
Yeah, thanks for the talk. I had a question about your science, not about your workflow. And I am not a climate scientist, so please tell me if any of my assumptions here are incorrect or misguided. But one of the things I think I understand about climate change is that the 1,000-year, 500-year, 100-year events of the last period are not necessarily those that we'll be seeing in the next 1,000 years. So I wonder, how do you adjust the analysis you're doing to account for the fact that those rare weather events are becoming a lot less rare? And how do you think about kind of predicting what that next 1,000-year event might look like?
Yeah, so I personally do not do any of this, but people in my group do. So they're able to do like pseudo global warming simulations with the like WRF, get new storms that haven't occurred in our record, but WRF outputs are gridded, and we have gridded precipitations data sets from WRF that you could then feed into a rainfall runoff model and get the outputs of what global warming would say storms are going to increase. So it's not perfect, but it does give you kind of an analog to what you might expect.
Okay, thank you.
So
Let's have a.
I got one.
Oh.
So all for DAGMan, but we may also want to consider improvements to Condor Submit. So that's me.
Thank you.
Okay, let's give a round of applause for Ben.